Welcome back. In this lecture, we're going to talk about gathering, classifying, and analyzing requirements as the first step in designing a large-scale system. But before we get into any details, let's first get some motivation. System requirements is just a formal word for figuring out and narrowing down what exactly we need to build for our client. As software engineers, we shouldn't be new to receiving formal requirements for the task we need to accomplish. But when it comes to the design of a large-scale system, there are a few differences from the usual requirements we are used to getting for implementing a method, an algorithm, or a class. The first difference is the scope and level of abstraction of the requirements, and especially the solution we need to design. For example, when we're tasked to implement a method or an algorithm in an existing codebase, we typically know what the input and output look like, and we're also somewhat limited to the programming languages we're going to use. As we go up to a more high-level abstraction, like designing a class, a module, a library, or an application, the range of possible ways to solve the problem becomes bigger and bigger as we have more degrees of freedom. Also, the scope of the problem becomes so high that it's hard for us to even visualize the implementation. So when we're asked to design an entire system, we may feel so overwhelmed that we may not even know where to begin. For example, imagine you're asked to design a file storage system, a video streaming solution, or a ride-sharing service that needs to scale to serving millions of users per day. It's hard not to get overwhelmed by such a task. The second challenge and difference from what we're normally used to is the level of ambiguity. The reason for this ambiguity is twofold. First of all, in many cases, the requirements are not even coming from an engineer, and sometimes they're not even coming from a very technical person. So the client or product manager may ask for something very high level, and it's our responsibility to transform those requests into precise and technical requirements. Those technical requirements will serve as the foundation for building our software architecture. The second reason for the high level of ambiguity is getting the specific requirements is already part of the solution. This may seem a little odd for us at first, but we have to remember that the client doesn't always know exactly what they need. The only thing they know for sure is the problem they need to solve. To demonstrate this, let's take a specific example. Let's say we're asked to design a hitchhiking service that allows people to join drivers that are already driving on a particular route and are willing to take passengers on their way for a fee. That may be all the requirements we get from the client, and it is up to us to ask things like, is it going to be a real-time service or the riders will have to contact the drivers in advance? Is it going to be a mobile or desktop experience, or maybe both? Are we going to enable payment through our system, or the riders will have to pay the drivers directly? In some cases, the client may not even know the answer to those questions right away, until we actually ask those questions. That is why, in most system design interviews, one of the things being tested is our ability to clarify and ask those questions ahead of time. Because as we can see, asking those questions and gathering those requirements is already part of the solution, and it greatly narrows down what we need to design and build. Now, what happens if we don't get all the requirements right? Can't we just do it incrementally? Why can't we simply build something and see if it satisfies the client? And if it doesn't, no big deal. We can just fix it, can't we? After all, we're not building a building or a bridge here. There's seemingly no big cost of materials in software, like in mechanical engineering, for example, or construction of a building. Well, the mental leap we need to make here from small projects like building a method or a few classes, where we can easily rewrite the code many times until we get it right, large-scale systems are big projects that cannot be changed easily overnight. Those projects take many engineers, sometimes even multiple teams of engineers. They can take months to build, which makes the cost of engineering time very significant. They also often require purchasing hardware and sometimes software licenses up front, and those projects typically involve contracts with time commitments and financial obligations. Also, not delivering the product to our clients or users on time may cause irreversible damage to our company's reputation and brand image, so getting the requirements right up front is absolutely critical. So now that we got the motivation for system requirements, let's take a step further and learn to classify the requirements into a few categories, which have completely different effects on our architecture and design. The three main types of requirements are features of the system, also known as functional requirements, quality attributes, which are also known as non-functional requirements, and system constraints, which are basically the limitations and boundaries of the system. Let's start talking about the first type of requirements, the features of the system. Those requirements essentially describe the system's behavior. In other words, what the system we're designing actually does. Those requirements are easily tied to the objective of the system. They are also called functional requirements because they essentially describe our system as a black box function. The user's inputs or external events are the inputs to that function, and the result or outcome of the operation taken by our system is the output of that function. It's important to point out that the features or functional requirements simply dictate the functionality of our system, but do not determine its architecture. And generally, any architecture can achieve any feature, which is what makes our job as software architects so difficult. Now, let's look at a few examples of features or functional requirements in our hitchhiking service example. One functional requirement can be as follows. When a rider logs into our mobile app, the system must display a map with nearby drivers within 5 miles radius. Here, the input to our system is the user's login action, and the output is the view of a map with nearby drivers. Let's take another example. When the ride is complete, the system will charge the rider's credit card and transfer that money to the driver minus some service fees. Here, the completion of the ride is the input event, and the transfer of the money is the outcome of the operation. Now let's talk about the second type of requirements, the quality attributes or non-functional requirements. The quality attributes are properties that the system must have as opposed to what the system must do. Examples of such qualities include scalability, availability, reliability, security, performance, and this list can go on and change depending on the system. In contrast to the functional requirements, the quality attributes do dictate the software architecture of our system. Another way to look at this is the software architecture defines the system quality attributes, and different architectures provide us with different quality attributes. The last type of requirements is system constraints. A few examples include strict deadlines, limited budget, or a small number of engineers that can work on our project. Such constraints may force us to make certain trade-offs and sacrifices in our design and shift us towards certain software architectural decisions that we would not make if we didn't have those constraints. The three types of requirements that we learned in this lecture are also sometimes referred to as architectural drivers, because they essentially drive our architectural decisions from an infinite universe of possibilities towards one solution that satisfies our client's needs. In this lecture, we learned about the importance of requirements in the design of large-scale systems. We discussed a few challenges of gathering those requirements, such as the large scope and the ambiguity that we may not be familiar with coming from a smaller scale programming world. After that, we talked about the risks of not getting those requirements correctly up front. And finally, we classified those requirements into three groups, which are also called the architectural drivers of the system. Those three groups are the features of the system, the quality attributes, and the system's constraints. See you guys all in the next lecture.